In this lecture, we want to discuss composite functions. The best way to understand this concept and to appreciate its usefulness is to look at a simple example from pure mathematics. Consider the function square root of x minus 2. This is a composite of two functions given by the respective formulas g of x is x minus 2 and f of u is the square root of u. So f of g of x is the square root of g of x, which is the square root of x minus 2. Now let's go over that again. To compute a value for x minus 2, this is the first layer of the composite function. Then we take the square root of this value, which represents the second layer of the composite function. We can represent that process with a mapping diagram. From the diagram, we see how a composite function works. It's just a sequence of successive mappings, in this case just two. We use the notation f circle g for composite functions. We have to be very careful when determining the domain and range of the composite function. To compute f circle g of x, or f of g of x if you prefer, we first must have x in the domain of the function g. Then f wants to map that number, g of x, into the final value of the function. This means that, and this is very important, g of x must lie in the domain of f. It sounds complicated, but if we go through the process for our example, you can see that it is just based on common sense. For our example, the first function, g of x equal x minus 2, has domain R. It's defined for all real numbers. However, the second function, f of u equals square root u, is only defined if u is non-negative. So we cannot compute the composite function unless g of x is greater than or equal to 0, i.e. x is greater than or equal to 2. Thus, the domain of the composite function is a set of all x to the right of and including 2, or if you like, the interval 2 to infinity. You can also see this graphically for this simple example. First, we graph g of x for x in R, its domain. Now notice that the range of g of x, which is the y values of the points on its graph, is all of R. The next function in our composite, f, operates on this range. That is, it's computing values based on numbers on the y-axis for the graph of g. The domain of f is only all negative numbers. So, and this is the important part, we must restrict the domain of the first function g so that its range is only the non-negative values. From the graph, you can see that the y values of points on the graph of g are non-negative when x is greater than or equal to 2. So the interval to infinity on the x-axis is the domain of the composite function. Let's do one more example to really nail this down. Consider the function square root of the quantity 2 minus root x. Let's find its domain and range. The function can be thought of as a composite of three functions, namely p circle q circle r, or p of q of r of x, with r of x equals square root x, q of u equal 2 minus u, and p of v equal the square root of v. Or we can be a little more efficient and consider it as a composition of two functions, f circle g, or f of g of x, where f of v is the square root of v and g of x is 2 minus square root x. We will use the second interpretation just because it has fewer levels to confuse us. To find the domain of this composite function, we need to find the domain of g, which is easy. G equals 2 minus square root x, so it's defined if and only if you can calculate square root x. So the domain is the interval 0 infinity including 0. I claim the range of g is the half-open interval minus infinity to 2, including 2. We can see this analytically, but looking at the graph is easier. We can convince ourselves that as x grows large, g becomes more and more negative, so the range, the y-axis values of points on the graph, is minus infinity 2. But the next function, f of u equals square root u, is only defined when u is greater than or equal to 0. So we have to restrict the domain of g so its range consists only of non-negative numbers. From the graph, we can see that this requires x to lie between 2 and 4, including the endpoints. To summarize this complicated situation, if we restrict x to the closed interval 2, 4, then the values of g of x will be non-negative, and then we can compute f of g of x equal the square root of g of x. So the domain of the composite function is 2, 4. What is the range? Well, we are asking for the range of f of g of x for x restricted to the interval 2, 4. From the graph of g of x, we see that the range of g for x so restricted is the closed interval 0, 2. Just look at the y values of points on the graph for x restricted to the interval 2, 4. So to compute the full composite function f of g of x equals square root g of x, we are computing the square roots of numbers between 0 and 2. So the range of the composite function is just the closed interval 0, root 2. Now you should find the domain and range of the composite function f of g of x equal square root sine x for x restricted to the closed interval 0 to pi. You should graph g of x equals sine x and determine its range, then determine how to restrict the domain of sine x so as to make f defined on that new restricted range. The answers are that the domain is the closed interval 0, pi, and the range is the closed interval 0, 1. Composite functions occur everywhere in the real world, and computer programmers in particular are always basing algorithms on the composition of simple functions. One example is a scholarship system which is based strictly on a student's grade point in the previous year. Assuming a perfect record is a 4.0 grade point average, one system might be to award $1,000 for a GPA between 3.5 and 3.7, $3,000 for a GPA between 3.7 and 3.9, and $5,000 for a perfect 4.0. Notice we didn't specify which award you get at the breakpoints because it just gets longer and messier to talk about it. It's easier to describe the system with mathematical formulas. To each student is assigned a unique student ID number, call it N. For each student, now identified as a number, there is assigned a grade point average, G. Then the scholarship awarded, cap S, is a function of the student number, and we can write a computer program which will automatically compute student awards based on the mathematical definition of the function S. Notice something strange. We wrote the rules as S of G of N because we want the computer to assign a scholarship to each student number N. But N does not appear in the definition on the right side. That's because S is in fact a composite function. First, we compute a grade point average, G of N, for each student number N. This is just another simple algorithm for the computer. To calculate G of N for a given student, multiply the student's mark in each course by the weight in that course, and add up all these products. Then divide this number by the sum of the weights. For example, if a student takes 10 one-term courses over the 2 terms in an academic year, getting grades G1, G2 through G10, and each course has a weight of WK, K equal 1 to 10, then G is given by the following formula. Having computed G of N, we can then compute the corresponding scholarship S. This is a classic example of a composite function evaluated by computing two or more successive functions in layers. In this example, the function g of n gave us a set of numbers in the range g between 0 and 4. Finally, we used a function f of u with domain the interval 0, 4, which computes the scholarship we want automatically. As you can see from this example, real-world composite functions can be complicated and time-consuming to work out in a lecture setting, so we will pretty much stick with pure mathematics examples to keep the important mathematical issues in sight. One last example. Let g of x be defined by sine x with domain closed interval 0, pi. Let f of u be defined as f of u is 2 for u between 0 and 1 over root 2, and f of u is minus 1 for u between 1 over root 2 and 1. Our task is to graph the composite function f composition g. The point is that f of u is defined piecewise using different formulas depending on the values of u, which are the values of sine x. So first, let's graph g of x equals sine x on 0, pi. Now, we're going to be computing f of g of x, and the formula for f depends on when the values of its argument, g of x, are above or below 1 over root 2. So let's add the horizontal line y equals 1 over root 2 to the graph of g. Now we can use this graph, combined with the definition of f, to determine the graph of the function f composition g. For x in the interval 0 to pi over 4, the values of g lie in the interval 0, 1 over root 2. So for x in this interval, f of g of x is 2. For x in the interval between pi over 4 and 3 pi over 4, we can see from the graph of sine x that the values of g of x equals sine x lie in the interval 1 over root 2, 1. So for x in this interval, f of g of x is minus 1. Finally, for x in the interval 3 pi over 4 to pi, the values of g of x equals sine x again lie in the interval 0, 1 over root 2. So the value of f of g of x is 2 for x in this interval. So at last, here's the graph of f composition g. Finally, I want to look at a set of elementary transformations that are often very useful in determining the graph of a function. Consider the simple polynomial f of x equals x cubed, which has the following graph. Now consider the polynomial g of x equals x minus 2 quantity cubed. This is just the composition of the translation map h of x equals x minus 2 with the function f of x equals x cubed. That is, g of x is just f composition h, or if you prefer, f of h of x. The graph is just the graph of f, translated, i.e. moved, horizontally 2 units to the right. The way to see this is to ask, when does f see argument 0 inside? For f of x, the function f sees the argument 0 when x is 0. For f of h of x, the function f sees argument 0 when x is equal to 2. In the same way, if p of x equals e to the x, then p composition h is just p of x minus 2, and that's, of course, e to the x minus 2, and the graph of p composition h is just the graph of p shifted 2 units to the right. The point is, this works for any given function and any constant. The graph of f of x minus c is just the graph of f of x, shifted c units to the right if c is positive, and it is just the graph of f of x shifted absolute value of c units to the left if c is less than 0. This shifted function is just a composite function. F of x minus c is just f composed with t, or f of t of x, where t of x is x minus c. We can also shift f vertically. The graph of f of x plus the constant c is just the graph of f of x, shifted c units upward if c is positive, downward if c is less than 0. This is also a composite function. F of x plus c can be thought of as v composed with f, or v of f of x, where v of x is just x plus c. In addition to translating a graph horizontally or vertically, we can change the scale, which is often called stretching the graph. For example, consider the function s of x equals sine x, and compare its graph with the graph of h of x equals sine 3x. The function s is periodic with period 2 pi, so the function h is periodic with 2 pi over 3. So, the horizontal axis has been compressed by a factor of 3. If we consider the function m of x equals sine of x over 3, then this function is periodic with period 3 times 2 pi, so we have stretched the x-axis by a factor of 3. In general, the graph of the function f of cx with c positive is just the graph of f of x, with the scale on the x-axis changed by a factor of c. The function f of cx is again a composite function. F of cx is f composition g, or f of g of x, where g of x is c times x. A sketch of the two functions which make up the composite shows us what is happening. The graph of the first function, g of x equals cx, is a straight line with slope c. So moving by 1 unit on the x-axis causes the image, g of x, to move by c units on the y-axis. It is this argument that the function f sees, and that is why the graph of f gets scaled. We can also carry out a vertical scale change. If we again start with s of x equals sine x and form p of x equals 3 sine x, we have just changed our vertical scale by a factor of 3. Let's look at an example to pull all of these ideas together. Consider the function h of x equals 3e to the 2x minus 1. We start with our old friend, the exponential function, g of x equals e to the x, and graph it. Then we change the horizontal scale by a factor of 2. Actually, we compress the x-axis by a factor of 2. Then we change the vertical scale by a factor of 3. Finally, we translate downward by 1. Now, to wrap up, we ask what happens when the scale factor is negative. That is, how does the graph of f of minus 2x relate to the graph of f of x? And how does the graph of minus 3 times f of x relate to the graph of f of x? Start with a simpler case. How does the graph of f of minus x relate to the graph of f of x? The answer is that the graph of f of minus x is just the graph of f of x reflected across the y-axis. So, for example, the graph of e to the minus x is just a reflection across the y-axis of the graph of e to the x. Then, the graph of e to the minus 2x would be the reflected graph with an x-axis scale change. Analogously, the graph of minus f of x is just the graph of f of x reflected across the x-axis. So, the graph of minus 3e to the x would be the graph of e to the x reflected across the x-axis, followed by a y-axis scale change. You can do these operations in either order. To sketch the graph of minus 3e to the x, you can first do the scale change on the graph of e to the x and follow this with a reflection as the following pictures show.